Sorry, I actually forgot to plug in my high definition microphone in the previous video. Now we have the microphone issue fixed. Let's continue. So as we've been talking about, we have now listed down the most generic form of our energy equation, or the energy balance of a system that has fluid flowing through, right? And let's take a look on how we will proceed from now on, okay? So if we kind of recall what we learned from fluid mechanics, we have deal about an equation of mechanical energy. So let's take a look at that first. So let's say from fluid mechanics, we've been dealing with fluid motion, right? So actually we have already talked about the equation of mechanical energy of flowing fluid. So we have the equation of mechanical energy. Okay, and what is exactly the equation of mechanical energy? I'm just going to write down it for you, but you're encouraged to kind of, derive it yourselves. So we have partial T. The mechanical energy term would be 1/2 rho v squared equals to negative gradient of the mechanical energy carried by the fluid minus gradient dot PV minus P times negative gradient of velocity minus gradient of shear stresses with respect to velocity. So work from shear forces, and we have minus gradient, and also we have external forces. Okay, so this is exactly the first term on the left hand side of our energy balance equation. So what we're going to do now is we're going to substitute the right hand side here into the right hand side of our energy balance equation. Okay, so what we're going to do here is we're going to subtract the equation of mechanical energy from the equation of energy. Okay, so next step would be you will be subtracting the equation of mechanical energy from equation of energy, so that we get the equation of internal energy. Okay, and so remember, our objective here is to obtain an equation or an energy equation which temperature appears, right? So if you think about each terms here, the kinetic term or the mechanical energy versus the internal energy is something that carries temperature, right? Because usually we think of internal energy will be equal to some constant volume heat capacity times some temperature differences. Or you think of the enthalpy term equals to the constant pressure heat capacity times temperature difference, right? So if we have a equation just having the internal energy or the enthalpy term, then it's going to be fulfilling our initial objective to have an equation where temperature appears. So that's why we're subtracting the equation of mechanical energy, because now on the left hand side we only have the internal energy term left. Okay, so if we do that, we now have the equation of internal energy that only has the internal energy term on the left-hand side, which equals to negative gradient rho u times v, this is a vector, minus gradient of the conduction minus p times delta v minus rho stress tensor, the dot product of the stress tensor with the gradient of the velocity. Okay, so we can look at each term by term here. So the first term, partial t rho u, this is the rate of increase in internal energy per unit volume. And then we have the first term on the right hand side, which would be the rate of increase in internal energy by convective transport. Okay. And also we have the gradient of Q would be the rate of increase in internal energy by heat conduction. Then we have the P gradient V term, which would be the reversible rate of internal energy increase per unit volume by compression. And finally, we have the dot product of the shear stress tensor with the velocity gradient would be the irreversible rate of internal energy increase per unit volume by viscous dissipation. So let's kind of go over these again. So I think I've been missing a velocity term here. Okay, so our objective here again is to try to have an energy equation of which temperature appears, which would be the most useful form for us. And we started by looking at an overall energy balance of the system. So we have the change of energy per volume. That includes the mechanical energy and the internal energy term here, equals to the gradient of the energy, combined energy flux vector, plus external forces, or the work that's associated with external forces, right? So what we're dealing here is basically just trying to expand all terms to come to our most generical form. So we have the accumulation of energy, which is the sum of the mechanical and internal energy, equals to the energy obtained by convection, by conduction, and also works associated with pressure forces, with viscous forces, and external forces. Okay, and then because we said that our objective is to try to get a energy equation that's associated with temperature, right? So we can actually try to take away the mechanical energy part by subtracting the equation of energy with the equation of mechanical energy. And we know this equation of mechanical energy from our fluid mechanics, which is right down here. Okay? So if we do that, you can see that some terms will be canceled out. And let's take a look at what terms are canceled out. The the convective energy, the convective transport of mechanical energy will be canceled out. Okay. The work by pressure force will be canceled out, will be subtracted. The work associated by viscous force also will be subtracted. And also external forces subtracted. Okay, so at the end, we've canceled out 3 terms. So 1, 2, 3. But we've introduced 2 new terms, right? So the 2 new terms are here. What we call the reversible rate of internal energy increase per unit volume by compression, and the irreversible increase by viscous dissipation. Okay, so we get to our equation of internal energy right down here. So we have on the left hand side the rate of increase in internal energy equals to that by convection, by conduction, the reversible change by compression, and the irreversible change by viscous dissipation. Okay, and this doesn't seem to be our final form yet, so we're going to continue. And how are we going to continue is by using what we've actually introduced before, or you've probably learned this before in your fluid mechanics, is introducing the concept of substantial derivative. Okay, so let's take a look at what is substantial derivative. Substantial derivative. Okay, so the substantial derivative is defined as the capital D over capital DT, which equals to partial t plus velocity, the dot product of velocity with some gradient of the property of interest. Okay, so for example, if you're looking at the substantial derivative of your internal energy, then it will look like du dt equals to partial u partial t plus v dot gradient u. Okay, so using this definition, we are going to try to further, clarify the equation of internal energies to a more useful form. Okay, so let's get started. So again, if we look at our equation of internal energy, let's kind of copy paste that down here. So let's copy it, copy, and let's paste it down here. Okay, so how are we going to use the idea of substantial derivative here? Let's do this step by step. Okay, so first let's look at our convective transport term. We can actually decouple these 2 terms. So the convective transport, the dot product of rho, u, and v actually can be decoupled. So it equals to v dot product of the gradient rho u plus rho u times the gradient of velocity. Okay, so by doing this, you see that this term with our left hand side will become the substantial derivative because we have a negative sign here. So if we do that kind of reorganization, we have partial t rho u plus v dot the gradient of rho u now equals to the right hand side. Okay. Maybe I should do this again. So plus the gradient of rho u and v equals to partial t rho u plus v times the gradient of rho u sorry, made a mistake here, so let's redo this again. So we need to do the derivative of each term adequately. So first, on the left hand side for the partial derivative, we can now say this equals to rho partial u partial t plus u partial rho partial t. Okay, plus v dot gradient rho u plus v dot gradient rho u and plus u gradient rho v. Okay, and if we kind of organize this again, we have the substantial derivative of u over t. That's the combination of this term and this term. And then we also have the other terms grouped together. So we have u times partial rho partial t plus gradient rho v. Okay, and the interesting part is if you look at the second term here within the parenthesis, this actually would equals to 0 because this is actually the equation of continuity. Okay, so by combining the convective transport term with the left-hand side, we are left with just the substantial derivative term. Okay, so now we have our equation being simplified to rho times the substantial derivative of the internal energy equals to the gradient of heat conduction minus the reversible change in internal energy by compression minus the irreversible change by viscous dissipation. Okay, and whenever you see this term of internal energy, also appearing with the pressure term, you naturally think of enthalpy term, right? So, if we continue here, let's continue our discussion, right? So, you know that from thermodynamics, the internal energy plus so this is internal energy per volume, plus the PV work per volume, so it's exactly P over rho. This actually equals to the enthalpy per unit volume, so H cap. Okay, so in other words, rho U plus P will equal to rho H cap. So we're going to use this this concept objective is to, let's say objective is to get a equation of enthalpy. So no need to deal with pressure term anymore. Oh, that's not exactly accurate, but you'll see what's going to happen later. Okay, so let's continue. So we're trying to combine the two terms with the internal energy and the pressure term here. So before we do that, we must define the substantial derivative of pressure. So we have the substantial derivative of pressure dP dt equals to partial P partial T plus V dot the gradient of P, right? This is by definition. Okay, so again, if we think about the substantial derivative of enthalpy, so d dt times rho h would now equal to rho substantial derivative of h t plus h times the substantial derivative of rho t. And this equals to d dt times rho u plus p, which equals to rho d u dt plus u d rho dt plus dp dt. Okay, so if we rearrange this, we get the rho substantial derivative of enthalpy over time equals to rho du dt plus dp dt minus h minus u d rho dt. So this equals now to what? To rho du dt plus dp dt minus p over rho times partial rho partial t plus v gradient of rho. And again, remember the substantial derivative of the density here is going to be 0 based on the equation of continuity. Again, equation of continuity. Okay, so if we keep on deriving this, made a small mistake again, so we need to be very careful here. So let's rewrite this. So up to this point, we're all corrected, but if you look at the equation of continuity, the equation of continuity states partial rho partial t plus gradient of rho v equals 0. So that means partial rho partial t plus v partial rho plus rho partial v equals to 0. So partial rho partial t plus v partial rho, p gradient of rho equals the substantial derivative of rho over t and equals the negative rho gradient of v. So substitute this into here, we now have this equals to rho substantial derivative of internal energy plus the substantial derivative of pressure minus P over rho times rho, negative rho times gradient of V. We now have our final form, which is partial rho substantial derivative of enthalpy equals to rho times the substantial derivative of internal energy plus dP dt plus P times the gradient of V. Okay, and we are going to substitute this back into our internal energy equation. So again, we can kind of paste that for you. Let's see if we can paste that for you here again. So paste. Yep, here we have it. Or maybe not this one, sorry. We should paste another one. So we've ended, I think, right here, right? So let's paste that again down here. Okay, so you can see where we're heading is that if you look at the term, this internal energy is here, also here, the PV term is here, and also here. So we're going to substitute these two terms by the enthalpy and the substantial derivative of pressure. So finally, we get the original equation becomes rho dH dt equals to negative gradient of the heat conduction minus the change by viscous dissipation plus the substantial derivative of pressure with time. Okay, so this is approaching our most generic form of the energy equation that's related with temperature. Okay, now let's continue our discussion for different cases. Okay, so if we're dealing with Newtonian fluids, so for Newtonian fluids, we know that the enthalpy would be a function of pressure and temperature. So the left-hand side, rho substantial derivative of the enthalpy will equal to rho times the constant pressure heat capacity times the substantial derivative of temperature, plus this is the pressure independent term, and the pressure dependent term we have rho times the molar volume minus T partial V partial T at constant pressure times the substantial derivative of pressure over time. Okay, so we can kind of rearrange this to have rho Cp, substantial derivative of temperature, plus rho times, this would be 1 over rho minus T partial T times 1 over rho at constant pressure dP dt. And that equals to rho Cp dt plus 1 minus partial natural log rho over partial natural log T P times dP dt. Okay, so if you subtract this back to our equation, you can see that the dP dt terms drops out from here, and we get, let's say, substitute back to equation. We have rho Cp dt equals to negative gradient of heat conduction minus heat dissipation by viscous dissipation minus partial natural log rho, not P, sorry, rho natural log T at constant pressure dP dt. So this would be our final form of equation of change of temperature in terms of Q and rho. So in terms of heat conduction and viscous dissipation. So we will stop here for now and we'll continue later on. So I will pause for now. We're going to discuss about the different cases and how we simplify the equation of change of temperature later on.